Homework solution 4.6, the field current of the generator in problem 5 is adjusted in each of the following scenarios to achieve rated voltage at full load conditions. What is the efficiency of the generator at rated load? What's the voltage regulation of the generator if it's loaded to rated kVA with 0.8 power factor lagging? What's the voltage regulation if it's loaded to rated kVA with 0.8 power factor leading? And what's the voltage regulation of the generator if it's loaded to rated kVA with unity power factor? So again, the givens here, we've got rated conditions. That's S3 phase is equal to 200 kVA. That's from the previous problem statement. The terminal voltage was 480 over root 3. The armature resistance is 0.03 ohms, and the armature reactance is 0.25 ohms. So that's what was given in the problem statement. We were asked to find the efficiency of the generator at rated conditions, so that's eta rated. Right. The voltage regulation, symbol for that is capital VR. At I rated, power factor equals 0.8 lagging. The voltage regulation at I rated, power factor equals 0.8 leading. And the voltage regulation at rated current and power factor equals 1. So basically what this is saying is what was the efficiency in the generator under the conditions we analyzed in the last problem, right? So the last problem analyzed the generator at under rated conditions. So we're just being asked, well, what was the efficiency there? And then what's the voltage regulation of the generator at 0.8 power factor lagging load? So that's also the previous problem. So, and the question is, how much change in terminal voltage was there? So then we want to repeat that for the two different loading conditions. So the solution to this is we just need to know how to calculate efficiency, and for that, that's just the output power divided by the input power times 100%. Well, we want to do this for rated conditions, and fortunately we already calculated those values. P out we calculated in the previous problem as 160 kilowatts. And we calculated Pn as 175.208 kilowatts. Right, so this was the power output. 200 kV at 0.8 was the rated condition, so that ends up being 160 kilowatts. And then the Pn, we took account the efficiencies, and remember the efficiencies were at rated conditions, so that's where that number comes from. So anyway, you do that math, you just divide 160 by 175.208, multiply by 100, and you get 91.32%. Now this is the efficiency of the generator, not of the entire system. This doesn't take into account any of the losses of burning the fuel and getting the turbine to spin. This just is, once the turbine is spinning, how much of its energy contained in its rotational motion actually gets transferred into output power. So this is kind of its electromagnetic conversion efficiency, 91.32%. So that's part A. Part B is voltage regulation. And I'll use the system diagram to explain that concept again, or the system model, electrical model of the system. So what happens is you've got the generator configured to provide VT under certain loading conditions, and by by that, what I mean is that there's going to be a voltage drop here, so you have to set EF appropriately to get rated voltage depending on what your load current is. So you have to adjust EF for all the different load currents to get the correct VT. So once VT is set, if you remove the load, it would change to a no load condition. And the difference between the no load condition and the loading condition is called voltage regulation. It's what percent voltage changes there under the load. So to quantify that, we have the quantity voltage regulation. It's the magnitude of the voltage at the terminal under a full load. Sorry, not under full load. Under a no load condition minus the magnitude of the voltage under a full load condition divided by the magnitude of the voltage under the full load. So it's the percent change in voltage. Convert that over to a percent by multiplying by 100. And the no load condition is just also equal to EF. So if IA is 0 here, that's a no load condition. EF and VT have to be the same because there's no voltage drop right here. So in part 5, we found that EF was equal to 321.97 at an angle of 7.81 degrees. And we know that if we're supplying rated voltage, that VT is equal to 480 over root 3 at an angle of 0 degrees volts. So those are the values we substitute in here, and we find that at rated conditions, the percent voltage regulation is going to be 312. Oh no, sorry, I made a typo right there. That's not 312, it's 321. Hopefully you guys caught that already. 321.97. There we go. So this is going to be 321.97. I'm just rounding to 322 minus 480 over root 3 divided by 480 over root 3. So that gives us the conversion. And so it's about 322 minus 277 over 277 times 100%. So we've got a voltage change under load of about 16.25% from the no load condition. So on to part C. So now we're not operating under rated conditions. The conditions are changing. So what is the voltage regulation of the generator if it's loaded to rated kVA with 0.8 power factor leading? And so what that is saying is we haven't done any adjustments to EF at all. Sorry, that's not correct. The problem statement says that the field current is adjusted in each of the following scenarios to achieve rated voltage. So we're adjusting EF, and we're looking at changes to the terminal voltage. So in each of these cases, we need to recalculate EF because terminal voltage is being delivered at rated voltage, and that's achieved by adjusting EF here. So VT is staying constant, EF is changing in this problem statement, and I know that because of that sentence right there. So sorry about that. This isn't one to scroll for some reason. Okay, there we go. So in part C, what I need to do is I need to recalculate what EF needs to be to maintain VT constant under this new loading condition. And so EF is just going to be equal to the terminal voltage, which was 480 over root 3 or 277 volts, plus the current that's flowing in here. So we know that rated current from Actually, we didn't calculate rated current in this example, but we did in the previous example. So if you go back to your numbers for problem number 5, you should find that the rated current amplitude was 240.563 amps. And this is going to be at a power factor of 0.8 lagging, so the inverse cosine of 0.8 gives you 36.87. Throw that minus sign on there to make it lagging. So that's IA. And then we need to multiply by the generator synchronous impedance, which was 0.03 plus J 0.25. Synchronous impedance ZS. So just a little application of KVL there. Oh, we're doing part C. Part C asks what's the voltage regulation of the generator if it's rated kVA with 0.8 power factor leading. So it'd be a plus sign. The lagging load is what we just analyzed. So just have to solve this equation for EF. That's 252 at an angle of 12 degrees volts. That gives us EF, which we know substitutes in for the no load voltage right here. Full load voltage isn't going to change because we're adjusting EF in this problem statement. So voltage regulation is going to be 252 minus 277 over 277 times 100%, negative 9.03%. So we get a negative voltage regulation for the leading load. Very common for leading loads. Actually, leading loads will always have a negative voltage regulation associated with that. Just highlighting the voltage regulation there for the lagging load. And then part D, it was for unity power factor. And so that's the same formula, EF equals 480 over root 3 plus, we're at rated power, so that means we're delivering rated current, but we're at a power factor of 1, which means its phase angle of the current is 0, and then 0.03 plus J 0.25 for the synchronous impedance. And so we get a value of 290.636 at an angle of 11.94 degrees volts. Voltage regulation of the system is then 290.64 minus 277 over 277 times 100% is 4.92% voltage regulation at a unity power factor.